In this video, I'm going to continue my previous lecture on Fanchel duality. Let me first recall what we did from last time. We consider an optimization problem in which we would like to minimize the function 5 given by f plus the composition of g and a. Over here, f is a function from Rn to the extended real line. A is an m by n matrix, and G is a function from Rm to the extended real line. Its Fanchel dual is the following optimization problem. Maximize phi of y, which is minus f star of A transpose times y minus G star of minus y, where y runs in Rm. And here, f star is the Fanchel conjugate of f, and G star is the Fanchel conjugate of G. We also define P by the optimal value of the primal problem. So P is the infimum of phi of x, where x runs in Rn. And we also let D be the supremum of psi of y, where y runs in Rm. And last time we proved the weak duality theorem, saying that the optimal value of the dual problem is always less than or equal to the optimal value of the primal problem, meaning that D is less than or equal to P. And in today's lecture, I'm going to talk about the strong duality theorem, in which we're going to establish some sufficient conditions not guarantee D is equal to P. Before getting to the Fanchel strong duality theorem, I'm gonna recall two important results from my lecture on Fanchel conjugate calculus. This is the Fanchel conjugate sum rule. Here we consider two convex functions from Rn to the extended real line under the condition that the relative interior of the domain of the function f intersection the relative interior of the function h is non-empty. We get this nice Fanchel conjugate sum rule. That means the Fanchel conjugate of f plus h at y is equal to the infimal convolution of the Fanchel conjugate of f and the Fanchel conjugate of h at y for all y in Rn. And one particular case is when y belongs to the domain of the Fanchel conjugate of the sum of f and h. That means this is a real number. Then the infimum in the definition of the infimal convolution here is attained in the sense that there exists y1 and y2 in Rn such that the sum of y1 and y2 is y, and alpha being this sum is equal to f star of y1 plus h star of y2. And again, the detailed proof of this theorem is given in my lecture on Fanchel conjugate calculus. The second important result is the Fanchel conjugate chain rule. Here we consider an m by n matrix A and a convex function G from Rm to the extended real line under the condition that there exists some x bar in Rn such that A times x bar belongs to the relative interior of the domain of the function G. Then we have a very nice Fanchel conjugate chain rule for the composition. So here, this is the Fanchel conjugate of the composition of G and A at U. It is the infimum of G star of V, and the infimum is taken on all V in Rm such that A transpose times V is equal to U. So over here, A transpose is an n by m matrix, V is in Rm and U is in Rn. If U belongs to the domain of the Fanchel conjugate of the composition, that means this is a real number. Then the infimum here is attained in the sense that there exists some V in Rm such that A transpose times V is equal to U, and alpha being this number, the Fanchel conjugate of T composed with A at U is actually the Fanchel conjugate of T at V. Okay, so again, we proved this in my lecture on Fanchel conjugate calculus. These are very important results that we're going to use in order to prove the Fanchel, the strong Fanchel duality theorem. And I also want to mention that in the case where G is a real value function, that means G is a function from Rm to R, then this condition is always satisfied because the domain of G then is Rm, and so this condition is always satisfied. Okay, and similarly, in the Fanchel conjugate sum rule, if f and h are real valued functions, then the relative interior condition is also satisfied. Now we are ready to talk about the strong duality theorem. In this theorem, we consider two convex functions f and g. F is a function from Rn to the extended real line. G is a function from Rm to the extended real line. And A is an m by n matrix. Now we suppose that the intersection of the relative interior of the domain of the function g and A of the relative interior of the domain of the function f is non-empty. This condition can be written in this way. 0 belongs to the relative interior of the domain of g minus A of the domain of f. Then the strong duality holds, meaning that P is equal to D. And again, let me emphasize some remarks. Now, if f and g here are real value functions, that means they are functions from Rn to R and Rm to R, then the domain of the function g here is the whole Rm. So the relative interior is the whole Rm. And similarly, the relative interior of the domain of the function f here is the whole Rn, and therefore this condition is always satisfied. Okay, and equivalently, this condition is always satisfied. However, it is very useful to use extended real value functions, as we're gonna see in our examples afterwards. Okay, so now we are going to prove this theorem. Recall that the function 5 is equal to the sum of f and the composition of g and a. Okay, and from the weak duality, by the weak duality theorem, we always have that D is less than or equal to P. That means the optimal value of the dual problem is always less than or equal to the optimal value of the primal problem. Okay, so now we will show that P is less than or equal to D. Okay. Now let's consider two cases. Case 1. In case 1, we suppose that P is equal to minus infinity. Alright, so we suppose that P is equal to minus infinity. Then this inequality is always satisfied. In this case, we can say obviously P is less than or equal to D. Okay, so in the second case, we suppose that P is greater than minus infinity. Okay, then it is easy to see that P is a real number. Okay, this is very easy to see because P is actually the infimum of 5 of x, where x runs in Rn, and under the hypothesis made, we see that 5 here is a proper function, that is an element in the domain of the function 5. So this optimal value is always less than minus infinity. Okay, so in this case, P is a real number. Now recall that P is actually the infimum of 5 of x, where x runs in Rn, and it is equal to minus 5 star of 0. This was proved in my previous lecture. Okay, so then let's look at minus P. So minus P is equal to 5 star of 0. Okay, and 5 is actually the sum of F and the composition of G and A. So we have this. Now, because P is a real number, this is a real number, meaning that 0 belongs to the domain of this Fanchel conjugate. So by the Fanchel conjugate sum rule, this sum can be written as F star of minus U plus G composed with A star of U for some U in Rn. Okay, and now we can apply the Fanchel conjugate chain rule to have that this is equal to F star of minus U plus G star of V for some V in Rm such that A transpose times V is equal to U. So again, this follows from the Fanchel conjugate chain rule formulated earlier. So now we're going to substitute in and get this. Then minus P is equal to F star of minus U. Minus U is actually minus A transpose V plus G star of V. Alright? And so from here we can write P as minus F star of minus A transpose times V plus G star of V. Okay? So this one can be written as minus of F star of A transpose times W. By the way, this is minus. Okay, minus G star of W, of minus W, sorry, where W here is equal to minus V. Okay, so this is always less than or equal to, this is always less than or equal to the supremum. This is always less than or equal to the supremum of minus F star of A transpose times Y minus G star of minus Y, where Y runs in Rf. Okay, because over here W is one element, and this is the supremum taken on all Y in Rf. And by the definition, this is exactly the optimal value of the dual problem D. Okay, so we have completed the proof that P is less than or equal to D. And again, by the weak duality, D is less than or equal to P. So in this case, P is equal to D. So therefore, P is equal to D. And so the duality holds. Now I'm going to talk about some important remarks. Remember that the function 5 can be written as f plus h, where h is the composition of G and A. And in the proof of the Fenchel strong duality theorem, we use the Fanchel conjugate sum rule for f and h. And at the same time, we use the Fanchel conjugate chain rule for the composition of G and A. And note that under the assumption made, that means this relative condition, relative interior condition is satisfied, then we can prove that this relative interior intersection this relative interior is non-empty. And at the same time, there exists some x bar in Rn such that A of x bar belongs to the actually here the relative interior of the function G. So we can apply both the Fanchel conjugate sum rule for f and h and the Fanchel conjugate chain rule for the composition of G and A. So that is an exercise, we can work it out at home. Note that there are some other forms of the Fanchel dual problems. Okay, so instead of maximizing this function, we can replace y by minus y and come up with this maximization problem. Okay, so we can solve this optimization problem by maximizing minus f star of minus a transpose times y minus g star of y, where y runs in Rm. And to solve this problem, we can solve a minimization problem, that is minimize f star of minus a transpose times y plus g star of y. We just simply replace, if we want to maximize a function psi, we can minimize minus psi. Okay, so we can solve this problem by minimizing minus psi. So it depends on the problem. We can pick appropriate form of the Fanchel dual problems. Now I'm going to talk about the third important remark. Sometimes we have to minimize a function 5 given in this form. So 5 of x is the sum of f of x and g of ax minus b, where x runs in Rn. And here f is a function from Rn to the extended real line, g is a function from Rm to the extended real line, A is an m by n matrix, and b is in Rm. So the difference between this form and the previous form is that we have minus b over here. Okay, so how can we formulate each Fanchel dual problem? We can use a very simple way to convert this problem to the original one. So we're going to define a new function in this way. g1 of x is just g of x minus b, where x runs in Rn. Okay, so then we can see that 5 of x is the sum of f of x and the composition of g1 and a, and this is true for all x in Rn. Okay, so let me go ahead and write down the is Fanchel dual problem. Okay, so then the Fanchel dual problem is maximize minus f star of a transpose times y, okay, minus g1 star of minus y, where y runs in Rm. Okay, how can we represent g1 star of minus y in terms of the original one? Okay, so please remember the simple Fanchel calculus from my previous lecture. So we can easily find the Fanchel conjugate of g1 in terms of the Fanchel conjugate of y. Okay, so we have that T1 star of y is always T star of y plus the inner product of b and y. Okay, so we can easily prove this, and this is true for all y in Rm. Okay, and again, if you would write down the formula for the Fanchel conjugate T1, we're gonna get this, and actually we proved in our previous lecture. So now I'm going to substitute this formula to this formula here and get the following problem. Then we can see that T1, the Fanchel conjugate of T1 of minus y is equal to T star of minus y minus the inner product of v and y. We just simply replace y by minus y. So each Fanchel dual problem now can be written as follows. We want to maximize. The first part is minus f star of A transpose times y, and the second part is minus T1 star of minus y. So it becomes minus T star of minus y. This minus becomes plus by, where y runs in Rm. Okay. So this form is sometimes very convenient, and we're gonna have some examples in which we're gonna apply this form instead of the original one. Now, one more thing, remember that if we consider the primal problem in this form, then a natural question is, under what condition the strong duality hold? And the answer is very simple. It's very similar to the original case. We can easily show that if the intersection of the relative interior of the domain of G and B of the relative interior of the domain of the function f is non-empty, where B of x is ax minus b. So this is B of x. Then the strong duality holds. Okay, and the proof is very simple. It follows directly from the Fenchel strong duality theorem. Now I'm going to present some examples in which we use Fanchel duality to solve some class of optimization problems. In the first example, we would like to minimize f of x subject to ax is equal to b. This is a constraint optimization problem where f is a function from Rn to the extended real line. A is an n by n matrix and B is an element of Rm. So our idea is to convert this constraint optimization problem to an unconstrained optimization problem using the so-called the indicator function. Okay, so recall that this is the indicator function associated with omega. Delta omega of x is infinity if x doesn't belong to omega, and delta omega of x is 0 if x is in omega. Okay, so over here we're gonna convert this constraint optimization problem to an unconstrained optimization problem in which we wanna minimize f of x plus delta. This is the set 0 of ax minus b. So it's easy to see that x bar is a solution of this problem if and only if x bar is a solution of this problem, because if ax minus b is not equal to 0, this is infinity. So to minimize this function, we only need to minimize the function f on the set of all x such that ax minus b is equal to 0, meaning that this is 0. So this problem and this problem are equivalent. Okay, so in this case, we can apply the Fanchel duality for f of x plus g of ax minus b. And what is the function g in this situation? here g of x is just delta, you can write g of y fine. G of y is delta associated with the indicator function associated with 0 of y. And x here is in Rn. Okay, so now we are ready to formulate each Fanchel dual problem. Now our problem is to minimize f of x plus delta of 0 of ax minus b. So it has this form where t of x is the indicator function associated with the singleton set 0. Okay, so now each Fanchel dual has this form. So I'm going to go ahead and write down. So each Fanchel dual is maximized. Over here we use minus f star of a transpose y. Okay, minus t star of minus y. Remember that the Fanchel conjugate of the indicator function associated with omega is actually the support function associated with omega. And recall that sigma omega of y is the supremum of the inner product of y and x, where x belongs to omega. Okay, so in this case, we're gonna get the support function associated with the set 0 of minus y plus by, where y runs in Rm. Okay, and the support function associated with 0 is 0. We can easily see that. So each dual problem is actually maximized minus f star of a transpose y plus the inner product of b and y. Very simple, where y runs in Rm. Okay. One more thing in this example, we would like to know under what condition the Fanchel strong duality holds. So the condition is 0 belongs to the relative interior of the domain of the function g minus b times the domain of the function f, where b of x is ax minus b. So note that g is the indicator function associated with the set 0. So the domain of the function g is 0, because outside of 0, the indicator function is infinity. So this condition can be written in this form, and we can easily see that it can be written in a very nice way. That is, b belongs to a of the relative interior of the domain of the function f. Now we are going to talk about a particular example. In this problem, this is a hyperplane in Rn. So this is the set of all x in Rn such that a transpose times x is equal to b. Over here, a is a vector in Rn and b is in R. Okay. So now let x be an element of Rn. How can we find the distance from x bar to this hyperplane? Okay, so we're gonna find the distance d from x bar to this hyperplane, and note that this is in R2, this is just a line. Okay, so we can find this distance by solving the following constraint optimization problem. We would like to minimize the norm of x bar minus x, where a transpose times x is equal to b. Okay, and we can instead we can solve this optimization problem. We want to minimize phi of x, which is 1/2 times norm of x minus x bar square, subject to this condition. So writing in this way makes the problem easier because this is a differentiable function. Okay, and actually if x is a solution of this optimization problem, then it is also a solution of the problem in which we want to minimize this form, and vice versa. Okay, so to solve this problem, we use this optimization model, and now how can our idea now is to use Fanchel duality to solve this optimization problem. Again, now we want to minimize this optimization problem, and we use the Fanchel dual form we presented earlier. So in order to do so, we need to know how to compute the Fanchel dual of this function 5. Okay, so f of x is 1/2 norm of x squared, where x is in Rn. We can easily see that f star of y is 1/2 norm of y squared. Okay, and if you apply the simple calculus rule for the Fanchel conjugate presented in my previous lecture, you're going to see that phi star of y is 1/2 norm of y squared plus the inner product of x bar and y. Okay, and therefore let's go ahead and apply the Fanchel duality form to the problem we would like to solve. So in this case, A is just A transpose, that is an n by 1 matrix. Okay, and B is in R. Okay, B is in R. So then the dual problem is just a one-dimensional problem. Very nice. So that is the maximization problem in which we want to maximize f star. Over here, A transpose is just A. By the way, we used the column notation for A. So A is a column vector, A1, AN. Okay. So then the dual problem is maximize minus f star of AT. So T placed the row of y earlier, minus BT, where T runs in R. Okay. But what is it? We're going to plug in. This is just 1/2 norm of TA squared, we plug in, minus the inner product of TA and x bar plus TB. Okay. So this is just 1/2 norm of A squared times T squared minus T times the inner product of A and x bar plus TB. And remember that this is just A transpose times x bar. They are just the same. Okay, so this is just a one-dimensional problem. How can we solve this problem? We just compute the derivative of this function with respect to t, and we set it 0, and then we just use the Fermat's rule because this is a concave problem. Okay, so then we can see that t is actually this. Okay, and now we plug back to the objective function. We're gonna see that the optimal value of the dual problem is equal to the optimal value of the primal problem in this case, because you can check that the condition for the strong duality holds. Okay, and you plug in and you get this one. Okay, but remember that we do not solve the original problem, but we solve the problem where you multiply by 1/2 and then you square this norm. Therefore, the distance from x bar to this hyperplane can be computed by taking the square root of 2 times p. Okay, the square root of 2 times p. That is the absolute value of A transpose times x bar minus b over norm of A. And this is a very familiar formula to compute the distance from a point x bar to a hyperplane.